I'm very pleased to be back in the harness at the Royal Institution, and especially to participate in a birthday celebration for Nature magazine called Our Place in Nature, which is very reminiscent of the title of T.H. Huxley's book, Man's Place in Nature, or as Huxley would doubtless say today, humanity's place in nature, since he was, for his time, loath to embrace the sexist assumptions of the time. In thinking about Huxley, who also wrote the first article in Volume 1, Number 1 of Nature, I came upon the following quote from the book in question. Huxley wrote, "The question of questions for mankind, the problem which underlies all others and is more deeply interesting than any other, is the ascertainment of the place which man occupies in nature and of his relations to the universe of things. Whence our race has come, what are the limits of our power over nature and of nature's power over us, to what goal we are tending, are the problems which present themselves anew and with undiminished interest to every man born into the world." And as I say, I'm sure the sexist language would be gone were Huxley talking today. Huxley also in the same book had the following lovely image. He's urging us to divest ourselves of human chauvinist prejudices, especially on the anatomical connections between humans and the great apes, and says, "Let us endeavor for a moment to disconnect our thinking selves from the mask of humanity. Let us imagine ourselves scientific Saturnians, if you will, fairly acquainted with such animals as now inhabit the earth, and employed in discussing the relations they bear to a new and singular erect and featherless biped, which some enterprising traveler, overcoming the difficulties of space and gravitation, has brought from that distant planet for our inspection, well preserved, it may be, in a cask of rum." A very vivid image, in one of the few in which an astronomical metaphor helped Huxley in his argument. The progress in planetary science from Volume 1, Number 1 of Nature to today is truly striking. Then there were 8 planets known and a handful of other worlds, most of those known only as points of light. The first asteroid, for example, had been detected in that same 19th century. Today, we know 9 planets in our system, more than 70 moons, thousands of cataloged asteroids, and somewhere between 10 to the 12th and 10 to the 14th comets, and the number is growing daily. This nice mosaic prepared by the U.S. Geological Survey gives a feeling, by no means of all, of some. And if I can have the lights down, you can see some sense of the diversity of worlds, the terrestrial planets here, the Jovian planets here, some sense of their moons, a single comet here. The remarkable fact is that all of the planets known at the time that nature was founded and all of the moons have now been visited by interplanetary spacecraft, largely from the United States, but also from the former Soviet Union and from the European Space Agency. We have flown reasonably close by all of these worlds, orbited 3 of them, landed on 3 of them, in each case with robot exploratory vehicles, and humans, 12 of us, have explored one of those worlds. This is a typical early interplanetary spacecraft of the Mariner series, and this is merely a reminder of the extraordinary fact that humans have walked and left their footprints on the surface of the cratered moon, and in another aspect of the mythic technological accomplishments of our time, we have even converted human beings into moons of the Earth. There, as a result of this, is a new cartography in which other worlds are being mapped, which will someday doubtless be in the schools. This is a map of the Jovian moon Ganymede, and there are some 30 or 40 such maps that are now in existence. What we learn from other worlds has been, in many respects, startling, unexpected, and I would like, in the few minutes I have, to cover a few broad themes, and I apologize for doing so so briefly. One set of justifications for planetary exploration by spacecraft is not only the sense of exploration and discovery, the new physics and chemistry and geology, but also the fact that we can calibrate our own world by examining other worlds somewhat like the Earth that have taken a different path. And in particular, there are ways in which we can add to our store of knowledge about what dumb things not to do to the Earth by studying what has gone wrong in other worlds. So, for example, Venus, which has almost the same mass, radius, and density of the Earth and was long thought of as the Earth's sister planet, has a completely overcast sky. This is Venus in the ultraviolet in false color photography. Many of the pictures I will show you will be in false color photography. We now know the clouds to be a concentrated solution of sulfuric acid, and not an extremely clement environment, and the surface much worse. In this, these are two slices from a mosaic taken by one of the Soviet Venera spacecraft. You're looking at a surface which extends to the horizon here, and you can see a little patch of yellow. That is the underside of the sulfur-rich clouds of Venus. And the remarkable fact is the surface of Venus has a pressure of 90 bars, 90 times that of the surface of the Earth, and a surface temperature of 470 degrees Celsius. It is as close to hell as any place in the solar system, and despite what Zeldovich said, the temperatures in the early universe are much too hot to be hell. Venus is hell. A hell in which matter falls to pieces is missing the point. Now, why are there such, by the way, there's also hydrochloric and hydrofluoric acid as minor constituents in the atmosphere besides sulfuric acid. How could an Earth-like planet get to be so hellish? It's not because Venus is closer to the sun, because its clouds reflect so much more light back to space compared to the Earth, that Venus, despite being slightly closer to the sun, ought to be cooler in terms of mean temperature, not warmer than the Earth. The reason is that 90-bar atmosphere is composed mainly of carbon dioxide with small amounts of water vapor. That atmosphere is transparent in the visible, but almost entirely opaque in the infrared, serves as a blanket thermal insulation, keeping the radiation in, preventing the surface from cooling off to space, and in other words, providing a massive greenhouse effect. This is a cautionary lesson for us here. I'm not proposing that there was once a species of Venusians who insisted on driving fuel-inefficient automobiles, and what we see today is the result. But if anyone says that the greenhouse effect is a delusion of liberal college professors, which is sometimes said in the United States, we need only point that person to Venus to see a greenhouse effect gone awry. By the way, the greenhouse effect in the Earth's atmosphere is responsible for some 25 degrees Celsius greenhouse effect. Were the greenhouse effect not operating on the Earth, the mean temperature of the Earth would be well below the freezing point of water. The oceans would freeze and we would be dead. A little greenhouse effect is a good thing. You just don't want too much. Likewise, if we turn to Mars, we see, as ground-based observers had suspected, essentially from the time of Volume 1, Number 1 of Nature, a place that is in a different respect Earth-like, although somewhat chillier. What we have discovered is a surface which is completely recognizable. If there are no places in Britain like this, there certainly are in the western parts of the United States. The atmosphere is very thin by terrestrial standards, about 6 millibars. Again, largely carbon dioxide, but because of the thinness of the atmosphere, the greenhouse effect is very small. When the Viking spacecraft that took this picture settled down on Mars in 1976 and subsequent years, they were geared to a number of studies, one of which was to look for microbial life on Mars. There were 3 microbiology experiments and 1 gas chromatograph mass spectrometer to look for organic chemistry. You can see here at top left the sample arm which reached out into the Martian soil. At the right, you can see an extraordinary fact, namely that humans have performed civil engineering on a modest scale, I admit, on the surface of another planet. The Martian soil withdrawn back into the spacecraft, the experiments I talked about examining the material, and while some of the results are still somewhat equivocal, the prevailing opinion is that life was not found. The extraordinary fact is that organic matter was not found, even though we know that organic matter, for example, from carbonaceous meteorites, must be falling on Mars. And this null result is now understood in terms of the absence of a Martian ozonosphere. So there is no barrier between the antiseptic ultraviolet radiation from the sun and the surface of Mars, and the organics are quickly fried, not directly by the ultraviolet light, but by the intermediation of peroxides, superoxides, and the hydroxyl radical. Here again, we have a reminder of what not to do with the Earth. The ozonosphere is very fragile, brought down to the temperature and pressure of this room. It is about 3 millimeters thick, and it is all that stands between us and Martian surface conditions. A parenthetical number, the typical lifetime of a typical terrestrial microorganism above the Earth's atmosphere because of ultraviolet light is about 1 second. Now, in some ways we were disappointed, but in some ways we found things on Mars that no one had anticipated, one of which is a network of hundreds of ancient river valleys, and more recently evidence for lakes and even oceans. We can tell from the cratering statistics, about which I'll say more later, that the time in which Mars was much more clement, was warmer, had higher pressure, had flowing liquid water, was something like 4 to maybe 3.8, 3.7, 3.6 billion years ago. I'll use the American billion, which means 1,000 million. Now that is exactly the time that the origin of life happened on the Earth. We know that the origin of life is constrained in two directions. The earliest fossils are about 3.5 billion years old. There is some disputed but intriguing evidence from carbon isotopes of extensive biological activity, 3.8 billion years old. On the other hand, the late heavy bombardment of the Earth, which we can calibrate by the cratering record on the Moon, and returned the radioactive dating of returned samples from the Moon, sterilized the Earth repeatedly, and the cratering flux fell off exponentially with something like 100 million year E-folding time, meaning that before about 4 billion years ago, if there were oceans, they were repeatedly driven into space, and the net result of this is that there is a rather narrow window for the origin of life on Earth, centered at around 4 billion years ago, plus or minus maybe 100 million years, something like that. Now, there's no reason to think that that's not enough time for the origin of life. 6 days was a popular hypothesis once. But it's very interesting. On the one hand, it might argue, recognizing the difficulty of extrapolating from a single example, nevertheless, it might argue that the origin of life was somehow easy, that is, sitting in the physics and chemistry when conditions were appropriate. But it's most interesting also to find that in Mars, at precisely the time of the origin of life on Earth, had very similar conditions. And would you expect to find life on Earth and not on Mars in that period? And therefore, even if Mars is lifeless today, there's still some debate on that, the possibility that there are fossil forms or chemical fossils to be found on Mars is a most intriguing possibility. And let me just say that since all life on Earth is built on precisely the same ground plan, the same nucleic acids for heredity, the same proteins for catalysis, the same genetic code book for translating nucleic acids into proteins, we have only one kind of life on Earth, and the biologist is severely constrained to know what is possible, or to put another way, to distinguish the necessary from the contingent. Finding even a humble example of life on another planet would revolutionize biology in that respect. However, even if we're lucky enough to find microorganisms or their fossils on Mars, the situation is a little complicated because we now know that it is possible for hypervelocity impact collisions to transfer material from Mars to the Earth and from the Earth to Mars, and not to fry the samples completely. So if we found life on Mars and it was rather similar to life on Earth, we would have to consider the possibility that it's really terrestrial life that we are seeing. And you could argue that whether the amino acids are L or D should tell you which it is, which would mean you'd have one chance in 2 of distinguishing endogenous from exogenous life. Well, another enormous surprise for Mars was the discovery of vast shield volcanoes. This is Olympus Mons, larger than the largest volcanoes on Earth. This is, in fact, some, I'll use English units, 80,000 feet above its surroundings, about 3 times the height of the largest volcano on Earth. It is presumably not active, although volcanologists, a patient lot, are hoping. This is Jupiter's Galilean satellite Io, as observed by Voyager, and you can see here at the limb a great volcano going off. This is, of course, highly exaggerated color. There were 8 active volcanoes on Io as we flew by. I'd like to, the volcanism is different in style from the Earth. This is not silicate, but sulfur volcanism. The chemistry of the surface of Io seems to be sulfur chemistry. And I'd like to show you just one painting by the British artist David Hardy, representing Io in foreground, Jupiter with its thin ring in background, and the Galileo spacecraft, which will be arriving in the Jupiter system in December of next year, incidentally dropping an entry probe into the atmosphere of Jupiter. Again, on the issue of comparative planetology, we surely will learn, we have already learned, about terrestrial volcanism by examining the other styles of volcanism on other worlds. I want now to turn to a most interesting issue, and to many people unexpected, namely organic chemistry in the solar system, especially the outer solar system. Starting in the outer asteroid belt and continuing right through the solar system to as far out as we can measure, organic chemistry seems to be rife. The only comet we have, this is Triton, the big moon of Neptune, and despite the fact that there is an atmospheric pressure of a microbar, there are active dark plumes all over the surface, or at least all over this province of the surface, which are thought to be dark, fine organic particles, which through the spring and summertime heating of the surface ices vaporize, are carried by the vaporized ices up into the atmosphere until they are carried by the prevailing 1 microbar wind, which is unexpected in many respects. This is a European Space Agency image of the nucleus of Halley's Comet. You can see the jets of essentially ice particles and gas coming off, which will form the long and lovely tails. But the nucleus itself is extremely dark. It has a albedo or reflectivity of a few %, which is probably darker than anything in this room when the lights are on. By flying mass spectrometers through Halley's Comet, both the Giotto mission of ESA and the Vega 1 and 2 missions of the former Soviet Union found that something like 25% of the surface material from the nucleus of Halley's Comet being jetted off to form the coma are composed of complex organic molecules. And that is one hint of abundant organic chemistry in the outer solar system. There is a new category of asteroids that live in the Uranus and Neptune vicinities and beyond, the Z-type asteroids, which are extraordinarily red. They're the reddest objects in the solar system. They also are covered with organics. There are many solid body moons, that is, airless moons in the outer solar system, Iapetus of Saturn, for example, which are covered with organics. And we now know that the interstellar grains and gas are largely composed of organic, or have significant constituents of organic materials, including very interesting molecules, C11 molecules, for example, and many nitriles are found there. I'd like to spend a moment on one object in the solar system that my group has been particularly interested in. This is Titan, the largest moon of Saturn. You can see in this montage, this picture was made by scissors and glue technology. You can see Titan right here. And here is a Voyager 1 close-up of Titan. It is a moon with an atmosphere, a haze layer, and underlying clouds, which is another astonishment. The atmosphere is retained because the exosphere temperature is so cold that despite the lower gravity, the atmosphere does not escape. There are no breaks in the haze, and yet we know a substantial amount about Titan because of the Voyager spacecraft. For example, from a radio occultation experiment, we know from differential refraction of the radio signals sent back to Earth, the atmospheric structure, the surface temperature, and pressure. The temperature is about 95 Kelvin. The pressure is about 1.6 bars, but because the acceleration due to gravity is about 6 times less, there is something like 10 times as much gas in terms of molecules per square centimeter above the surface of Titan than above the surface of the Earth. Now, that's a very startling situation. Here is the atmospheric structure curve. You can see that the structure is rather similar in overall design to the Earth's, with an adiabatic lower atmosphere and an isothermal stratosphere. I've also indicated here 4 regions where electromagnetic and charged particle radiation is deposited in this atmosphere. Titan sits episodically, or better periodically, in the Saturnian magnetosphere, and the charged particles from the Saturnian magnetosphere pour into the atmosphere and ought to produce chemistry. A very interesting question is, what is that haze made of? And what about the minor atmospheric constituents? Here is an experiment, the first and most simple experiment we've done, in which we have an electric discharge in a simulated Titan atmosphere. The atmosphere of Titan is essentially mainly molecular nitrogen, as it is here on Earth, and a few % methane. And you can see, especially if the lights will go down for a moment, the interior of this flask coated with a material which, by accident, matches the picture of Titan, which happens to be, by the merest of coincidences, on the wall behind. This is not the means of determining that the material is the same. I'll show you in a moment how we actually do it. Here, briefly, you can see the minor constituents of the atmosphere, C2 and C3 hydrocarbons and nitriles. And by using the yields in such experiments and a one-dimensional eddy diffusion argument, we have been able to match the observed abundances, E means equator, P means pole, for all of these molecules. These C2 hydrocarbons are matched by ultraviolet photochemistry. We have measured the real and imaginary parts of the refractive indices of the powdery material I showed you in a moment ago, which we call Titan Tholin. You can see this goes from soft X-rays to microwaves, and about 4 orders of magnitude variation in the imaginary part of the refractive index. That's this solid curve. The cross-hatching here is International Ultraviolet Explorer, ground-based Earth observations, and Voyager infrared observations of the actual properties of the haze. And the material made in that flask matches within experimental error. Here is a material poly-HCN, which is one of many, polyacetylenes are another, proposed, which do not match. So now we have this stuff in a flask, and it's being made on the in the atmosphere of Titan. We can calculate what the sedimentation rate is, and at least tens and possibly hundreds of meters of this stuff has piled up on Titan during geological time. What is it made of? Well, we can examine it, and briefly, this is a list of biological and non-biological amino acids that we found on acid hydrolysis, racemic, of course. Here is, oh, it's upside down, but it's beyond the Rayleigh resolution criterion anyway. Nobody will be able to read it. Anyway, a wide variety of other organics, including pyrimidines and one purine, which suggests that materials important for life on Earth are being made in the atmosphere of Titan and settling down on the surface. You might think that this is going to be a very dry surface, that liquid water, an essential prerequisite for life and for pre-biological organic chemistry on the Earth, is wholly unavailable in that 95 Kelvin surface environment. However, cometary impacts, which are happening at a known rate, briefly, for something like 1,000-year periods, liquefy the ice on the surface, and something like half the surface of Titan has seen liquid water for something like 1,000 years. And so we now have the interesting question of, can organic chemistry have been carried still further in that liquid water? If the origin of life on Earth took 10 to the 8th years, could something along similar lines have happened on Titan in 10 to the 3 years? We have a nice bound, and it'll be very interesting to send spacecraft, entry probes, into Titan and do in situ organic chemistry. And here is a artist's conception, needless to say, of the European Space Agency's Huygens probe at the end of a parachute tether, about to settle through the reddish organic haze of Titan and land on the surface carrying a GCMS. And if all goes well and Britain's contribution does not slack, this will happen in the year 2004. I'd like now to move on to cratering. Here is the Earth and the Moon to scale, and also approximately to albedo scale, the Moon being much darker than the Earth. The Moon's large basins are produced by massive impacts in the past. That was part of the argument I used a moment ago about the Earth having been subject to such a heavy bombardment. This is another reminder about the heavily cratered surface of the Moon. That, of course, is the Earth, although every child on seeing that picture insists it's the Moon. Here is Meteor Crater, Arizona, a reminder that impacts occur on the Earth as well. The Earth has many fewer, of course, because of the preferential erosion of craters on the Earth due to running water and plate tectonics and other factors. Here is Miranda, a moon of Uranus, and you'll recognize this is an extremely odd-looking world. I mean, look at these boundaries. And Miranda and many other moons in the outer solar system appear to have been utterly destroyed, that is, demolished, by high-speed impacts, the fragments then reforming And some moons are thought to have been destroyed and reformed, phoenixes arising from the ashes 2 and 3 and 4 times. The rings of Saturn and the other 3 Jovian planets may have such an impact origin as well. Impacts are the story from Mercury to the Neptune system. The solar system has been the product of gross interstellar, interplanetary violence. This is a peek at the Cretaceous-Tertiary boundary. Cretaceous chalks at the top, clay layer crossing the picture diagonally, Tertiary sediments at bottom right, and this is done in Gubbio, the famous place where the Alvarezes first found the iridium anomaly, suggesting, now I think very widely accepted, that 65 million years ago the Earth was hit by an asteroid or comet about 10 kilometers in diameter. And the consequences of that must have been, if you did not take another look at the geological record, just cataclysmic. We now know from charcoal distributed all over the world in the sediment that something like the present global biomass of vegetation burst into flames. We know that the ozonosphere would have been enormously depleted. We know that fine particles from the impact were put up to stratospheric altitudes where they survived for some years, darkening and cooling the Earth. And this succession of assaults must have been extremely effective in causing extinction of species. And in fact, not only were all the dinosaurs rendered extinct in that period of time, but something like 75% of all the species of life on Earth. This is a reminder that it makes sense to pay attention to interplanetary collisions. Now, 65 million years ago, this is an artist's conception of the impact off Yucatan, and here is I have this for Steve Gould, a somber, you can see the expression, triceratops, wandering about a frozen wasteland of other dead confreres. And here is the ancestor of everybody in this room, a small mouse-like insectivorous nocturnal mammal. And if the Earth had not been hit by a 10-kilometer diameter asteroid or comet at that time, then we would all look extremely different. Doubtless consider ourselves very handsome. Here is the fragments of the Shoemaker-Levy 9 comet, which impacted each fragment, one after the other, dutifully impacting Jupiter the middle of July of this year. Here is a splendid picture of an impact in the course of happening. Here you can see an impact blemish from one of the early collisions, and this blemish is Earth-size, which gives a crude support to the proposition that a 1-kilometer object hitting the Earth will have essentially global consequences. I don't have time to go into the significance of this, but let me just give you one number. We know only a small fraction of the near-Earth objects that might collide with the Earth. Here is a tiny fraction of them. But there are something like 2,000 near-Earth asteroids, 1-kilometer diameter or more, and of which we have inventoried less than 10%. From the statistics, it appears that the probability that the Earth will be hit by such an object in the next century is a little less than 10 to the minus 3. The typical chance of dying in a single commercial airline flight is something a little less than 10 to the minus 6, and some people find that worrisome. 10 to the minus 3 is, by some standards, a large number, and what to do about it is a most interesting question. There's a double-edged sword here, which I will not go into. Finally, let me go to the outer solar system. Here is a particles and fields portrait of the solar system. The heliopause is the boundary where the wind from the sun is replaced by the wind from the stars. There are 4 spacecraft, Pioneers 10 and 11, Voyagers 1 and 2, which are headed towards the heliopause. We think we know where that is directly now. There is a chance that the 2 Voyager spacecraft will penetrate through the heliopause before their nuclear batteries fail somewhere around 2015 or 2020. These spacecraft are the fastest objects ever launched by the human species. They're headed, they have escape velocity from the solar system. They are destined to wander forever in the great dark between the stars. This is the Voyager spacecraft with an interstellar record on it. Greetings for another civilization, if they ever find it and can read it. One of the important findings that is happening in our time is the discovery of the circumstellar accretion disks from which almost certainly planets are being formed around other stars. This is Beta Pictoris. Not only accretion disks, but there now seems to be at least one bona fide extrasolar planetary system around a very unlikely object, the pulsar B1257 plus 12. It's very likely at the present rate of improvement of the technology that we will have an inventory of planetary systems around the nearest few hundred stars by the 150th anniversary of nature. My last slide. I had always wanted, with Voyager, to turn the cameras back from the outer solar system and photograph the Earth. It's a single pixel, but I thought that pixel would be worth looking at. And after we passed Neptune, I was able to get these pictures, and there is our planet, a pale blue dot. I look at that world, and I think that's where we are. That's where we live. That's where everybody we love, everybody we know, everybody we ever heard of, lived out their lives. The aggregate of all our joy and suffering, thousands of confident religions, ideologies, and economic doctrines, every hunter and forager, every hero and coward, every king and peasant, every young couple in love, every hopeful child, every corrupt politician, every revered religious leader, every scientist, every superstar, every supreme leader, all of us, everybody, every saint and sinner in the history of our species lived out our days there on a mote of dust suspended in a sunbeam. To me, it says that the Earth is a very small stage in a vast cosmic arena. I think of the rivers of blood spilled by all those generals and emperors and prime ministers and presidents, so that in glory and triumph they could be the momentary masters of a corner of a pixel. I think of the endless cruelties visited by the inhabitants of one corner of this dot on the scarcely distinguishable inhabitants of another corner of this dot, how frequent their misunderstandings, how eager they are to kill one another, how fervent their hatreds. And it seems to me that our posturings, our imagined self-importance, the delusion that we have some privileged position in the universe are challenged by this point of pale light. Our planet is a lonely speck in the great enveloping cosmic dark. And in our obscurity and all this vastness, there is no hint that help will come from elsewhere to save us from ourselves. It is sometimes said that astronomy is a humbling, and I might add, character-building experience. There's perhaps no better demonstration, to me it seems that way, of the folly of human conceits than this distant image of our tiny world. To me, it underscores, this is just a personal statement, our responsibility to deal more kindly with one another and to preserve and cherish the pale blue dot, which is the only home we've ever known. And T.H. Huxley had, this one last quote from Huxley, had a similar comment. He said, it seems to me it applies so well to this, "It is as if nature herself had foreseen the arrogance of man, and with Roman severity had provided that his intellect, by its very triumphs, should call into prominence the slaves, admonishing the conqueror that he is but dust." Thank you.